it's my pleasure to have Enxin Wu from Shantou University as our speaker today. Enxin graduated from Canada, is the same supervisor as our co-organizer Igor Hapkin, and then he spent a lot of time, 2 years postdoc in Vienna, but never visited Prague, and he only visited online in the Zoom seminar. Yeah. So today, Enxin Wu shall speak on smooth vector spaces. Please.
Yeah, thanks, Ben, for the invitation. And it's a great pleasure to see lots of friends here, especially Igor. Okay, so today I'm going to talk about diffeological vector spaces, or in other words, smooth vector spaces, because I need to talk a lot of stuff. So let me just start. Oh, wait. Okay, so first, let me start from a motivation example from function analysis. So there is a somehow well-known lemma called Boreal's lemma, which says for any smooth function f, if you take its derivatives from, I should say f0, f prime 0, f double prime 0, etc., and you evaluate them at 0, you get a map C infinity RR from all the smooth functions from R to R to the infinite product of R. This is clearly a linear map because all the derivatives are linear, and you get such a map. The amazing thing is this map is surjective. This is somehow called Boreal's lemma. And from the first site of this lemma, you will say, well, it's simple, right? Because if you know about these derivatives, you can somehow reconstruct this function via Taylor expansion. But the difficulty is this series is arbitrarily given, right? And if you write down simply the Taylor expansion, it does not necessarily converge. So you could not necessarily find a function with a given derivative as you constructed. But Boreal says, no, you can do some trick on it and you get the right answer. So that's called Boreal's lemma. And on the other hand, you can even, you can like generalize it, okay? So here is the generalization. It says, given any smooth function from U to R where U is some open set of some Euclidean space, or more generally, you can even make it a smooth manifold, okay? If you are given a sequence of such smooth functions, then there is always a smooth function G, which is whose domain is one-dimensional higher, such that its nth derivative of G with respect to this additional variable T. And you evaluated it at x0, you get back to this original, the given sequence of functions. So what does these results mean? I will answer it in the framework of diffeology. In other words, you will get a short exact sequence of diffeological vector spaces. So I will tell you what is a diffeological space, what are diffeological vector spaces. But up to now, we see that as vector spaces, you get a short exact sequence. You just take here, K is a kernel of this map, or in other words, K is all the smooth functions such that its value at 0 and all its derivatives at 0 are 0, which means it's flat at 0, right? Okay, so this is the first motivation for us. And another motivation is actually an interesting thing, which I found when I was trying to do some research on tangent space of diffeological spaces. So it could be translated into an analysis question. I think you guys are very smart. maybe you can directly find a solution to that. I just find an invariant for this result, and eventually I get the result. So let me just make some notations first. So let U, V, and UI be open subsets in some Euclidean spaces. They could be, I mean, different in different Euclidean space. Okay, and let U map to countable product of R. We call it smooth if each component is smooth. And we write I for all the smooth and injective maps from UI to the countable product of R. Okay. And the interesting result is there always exists a smooth function in this sense, from V to the countable product of R, such that there exists a point in V, and no matter how small neighborhood of this little v inside the V, no matter how small this neighborhood is, the Q restricted to V prime can never factor through these smooth injective maps. Okay, so it could not be written as the composition of Pi composed with Ri, where Ri are the usual because V prime and UI are open subsets in Euclidean spaces. So we can talk smoothness in the usual sense. So this result just says there exists such a smooth map, and there exists a point. No matter how small the neighborhood you get, you can never write it, factor through this map as a smooth map composed with injective smooth map. Okay, so this is a very, but you might say it's somehow complicated or strange, but it actually comes from the tangent space theory. So, but unfortunately, because I don't have much time, especially today, I'm going to focus more on the vector space thing. So I will not talk about this example, but you can, if you are interested, you can use the diffeology on the tangent space to prove this. Okay, so this is an infinite dimensional space. So the tangent space is also infinite dimensional. So from differential geometry, we usually study the vector space structure. But in diffeology, you can also put diffeology on this tangent space, this vector space. You have diffeology structure, and you can use this diffeology structure to prove this result. Okay, so this is my second motivation. So that means we can use diffeological vector space theory to solve some problems, right? So let me start by telling you what is a diffeological space. So a diffeological space is a set. So you can compare it with topological spaces. So topological space is a set with certain structure. So is diffeology. So it's a start from a set, and you equip it with certain maps from U to X. We call them plots, where the domain of the plots are open subsets in Rn, such that 3 more axioms are satisfied. The first axiom says every constant map is always a plot. Okay. The second one says if U to X is a plot, V to U is a smooth map where U and V are both open subsets in Rn. And then the composition is also a plot. And the third one says if you want to test something is a plot or not, it's local in the sense that you can find an open cover of U such that each restriction of this map to UI is a plot, then U is a plot. Okay. And this definition was introduced by a French mathematician. He's both a mathematician and a physician. His famous work is in symplectic geometry. And in the 1980s, when he was trying to study symplectic diffeomorphism groups, he wanted to talk about what kind of smooth structures are there. So he introduced this diffeological space theory. Okay, he is JM Surreal. Okay, so these are the basic objects we are going to study, and we need to talk about what are the maps between them. So it's easy to define because given two diffeological spaces, we have these structures. So a function, we call it smooth if the plots of the domain was mapped to the plot of the codomain. So this definition is extremely simple, right? And we have objects, we have morphisms, we get a category, and we denote it by diff. If you guys know some sheaf theory, you can see there are some kinds of sheaf inside it. So for example, you can translate the second condition into a pre-sheaf condition and the third condition into a sheaf condition. So it's related to sheaf theory, actually, this one. But in this definition, it's more like set theoretical or say more geometrical. So people are easier to understand. The most strange thing from sheaf theory is the first one. It says a constant map is a plot, which has another abstract meaning. It is called concrete sheaves. It means the underlying, you have an underlying set which can realize all the sections. So this is what it means. Okay. Okay, so why do we want to talk about the diffeological spaces? So first of all, it generalizes the category of manifolds. So manifolds are very important objects in mathematics. Everybody knows about it, right? And in abstract category theory language, it just says diff contains the category of smooth manifolds as a fourth subcategory. It means that every smooth manifold can be viewed automatically as a diffeological space in the following sense. So remember, a diffeological space is a set with some structures, and the structure are called plots. They are maps from open subsets to the diffeological space, to the given set, right? So given a smooth manifold, we take its underlying set, and the plots are taken to be the smooth maps. Okay, so let me just write a little bit. So for example, if M is a smooth manifold, and I take the underlying set as the diffeological space, and the plots, because these are open in Rn, right? These are open in Rn. So this is a manifold. So we can talk about smooth maps there. And it's a plot if and only if it's smooth in the usual sense. This is defined to be a plot, okay? So this would, in this way, you can easily check the three axioms of a diffeological space are satisfied. So this makes a smooth manifold automatically into a diffeological space. Moreover, given two smooth manifolds, M and N, so you can talk about the smooth maps between them in two senses. One is in the classical sense, another is in this new sense because they are all viewed as diffeological spaces. The amazing thing is they match. So you don't lose any information and then you do not add any more information. So it contains this manifold as a fourth category. It's a very nice generalization, very natural. Okay. Okay, another thing is on diffeological spaces, you can do many categorical operations. For example, it's called bicomplete, Cartesian closed. So bicomplete means you can take any limits, colimits, for example, the subspace, the product. And for colimits, you can take any quotient space or any, for example, the coproduct or push out, something like that. And the Cartesian closed not just means you can take a function space, just like what previously we had this C infinity RR. These can all be viewed because R and R are both manifolds. They can be viewed as diffeological spaces. Then the function space is also a diffeological space. And this function space is right adjoint to the product. So this is what called Cartesian closed. Okay. And another thing I want to clarify is you can view diffeological spaces as a generalization of manifolds in the following sense. So manifolds are gluing of Euclidean spaces via diffeomorphisms when you use the charts. And diffeological spaces, they can be viewed as gluings of Euclidean spaces, but via not diffeomorphism, but via arbitrary smooth maps. Okay. Another thing is, so this theory is a bit interesting. For manifolds, if you recall the definitions, you first have a topological space, then you put a smooth structure there, right? But diffeological space, the order is somehow opposite. You first have defined what a diffeological space is. It is a set with certain structure. And now after that, you get a topology, okay? We call it a D-topology. What is it? Because a diffeological space is a set and some plots, but these plots are from Euclidean space, open subsets in Euclidean space. So they automatically has the Euclidean topology. So now I give the target, the final topology with respect to all plots in the sense that A in X is open if and only if for every plot P, this P inverse A is open in U. So this is how I define the topology on the diffeological space. This is called the D topology. It was first introduced by Iglesias Lemma, and in his PhD thesis, he was Surreal's student. Okay. No, sorry. Okay, so furthermore, what's good for this D topology? It makes every smooth map between diffeological spaces to be continuous between the corresponding topological spaces. In functional analysis, you will always see some kind of like sentences or propositions, like some maps are smooth but not continuous. But now, if you view things in the category of diffeological spaces, you take the D topology, then every smooth map will automatically be continuous. Okay, when all these diffeological spaces are equipped with the D topology. So that's the key thing, right? And the most famous example in diffeology is something called irrational tori. So let me just roughly say a few words about it because it's so famous. So T alpha, first of all, you can take the two-dimensional torus. You modulo an irrational line there. From differential geometry, we all know that it's a dense line inside this T2. So after taking this quotient, you have no more topology there. So it's usually quoted as an example of immersion, but not embedding. Okay, so the irrational torus is taken to be this quotient. So you can see it has no more topology on there. And in the category of diffeological space, you can identify it with this space. So somehow you reduce the dimension by one, right? This 2-dimension modulo 1 dimension, it should be 1 dimension. So it's something like this. It's R modulo by Z plus alpha Z, where alpha is an irrational number. I should say irrational. Okay, I should say not quotient, but I should say its difference. Okay, sorry about it. Anyway, okay, so it has no topology. But the funny thing is this arithmetic alpha can somehow be reflected by the diffeological structure of T alpha. I'm not going to write down all the details, but let me just mention it by language. So it says alpha is quadratic irrational or not. It could be tested by the diffeomorphism group of T alpha. If it is irrational, quadratic irrational, the diffeomorphism group has one feature. And if it's not, it would have another feature. So it's very funny result, right? So this is a very famous result, not far from, it was found not far from the invention of the concept of diffeological space. It was done by Donato and Iglesias Lemma in the, I think, 85 or something. Both of them are students of Surreal. Okay. So another thing I want to mention
Sorry,
is,
Enxin, can I ask a
yes.
question?
Yeah, sure.
Just maybe running a little bit ahead. If
Okay.
you consider a Frechet manifold as a diffeological space, do you recover the Frechet topology from the D topology?
That's a good question. That's a good question. Actually, I have honestly I haven't checked, but
okay.
I think very probably it would. It would, because if you take the, for example, the manifold, definitely you can recover the classical structure. For Hilbert, I think you can also do the same. Banach Hilbert, Hilbert is easier to check. Banach is a bit. So how do you define the diffeology structure? So first of all, you need to make a suitable definition of it, because of Banach. So Hilbert, because you have the metric, so you can easily define what is a smooth thing, because you just compose it with the norm, then you can define it. But for the Banach, because you take a square root or something, right? It's basically at 0, you might got some problem, but you need a suitable definition with that. I think you can also get back to the usual topology. Usually the topology will behave not too bad, as long as it's the space is not too bad. It would not be too bad. But I think you asked a very good question. I would say it should be, but let me just check and I can email you back if I got the answer.
Okay, all right, thanks.
Okay, thanks for your question. Yeah. Okay, so another good thing is for all these spaces, although they are defined like kinds of like topological space, but you can still do differential topology, different geometry on every diffeological space. So it's a bit interesting. It enlarges the objects. But many things, just as you guys just see, you have to check again by hand, right? Unfortunately. Okay, so let me just quickly go to the field of diffeological vector space. I'm a bit far away from it now, right? So a diffeological vector space, so in short language, it's a vector space object in the category of diffeological spaces, or more precisely, it just means it's a vector space, both a vector space and a diffeological space, such that you would require addition and scalar multiplication to be smooth. Okay, so let's take some examples. For example, the Rn, it's a manifold, so it could be viewed automatically as a diffeological space. And of course, it's also a vector space, so you can check easily it's a diffeological vector space because the addition and scalar multiplication are both smooth. And you can also check that the product of diffeological spaces automatically diffeological space, no matter how many products you put on there. And also every linear subspace, you can give it a subspace structure on this space, and you get again a diffeological vector space. And so is a quotient. Any quotient vector space is a diffeological vector space. Moreover, you also get back to the function space. As long as the target is a diffeological vector space, the smooth map from arbitrary diffeological space to the diffeological vector space is a diffeological vector space. Okay, these are very concrete examples. So in particular, we still have this symphony RR, right? So I always want to mention about this. And this piece, I have an infinite product of R, right? The countable product. Okay, so Iglesias first studied these things because they were the first ones to introduce these concepts. So it's very natural to say what a vector space could have, what diffeology a vector space could have. So actually every vector space could have a smallest diffeology, making it into a diffeological vector space. Moreover, you can also have a largest diffeology on it. But the largest diffeology is usually not interesting. The smallest one usually could be viewed and used as an invariant. But in this talk, I will not get into these. Okay, I will just give you a more general theory. Okay. And diffeological vector spaces and smooth linear maps. By smooth linear map, I mean both a linear map and a smooth map in the sense of diffeology. And you get a category I denoted by DVS. So here, my convention is when it's an object, I use small letters. When it's a category, I use big letters. Okay. And you can check this category, it's complete, co-complete. I should say it's bicomplete. And it's additive, but not abelian. Okay. So then somehow you should be able to do some homological algebra on it. I think because the seminar is also called the cohomology something, and I think homological algebra, this concept is suitable for this talk. So let me go to exact sequence. Starting by exact sequencing. Sorry, there is one more S here. So first, let me define what a short exact sequence of diffeological vector space is. So it's very natural. Everybody could think about it. It's a sequence of diffeological vector spaces. If, first of all, it's a short exact sequence of vector spaces in the sense that this map is surjective or epimorphism. This map is injective, and the kernel is equal to image here. This kernel equal to image here. And moreover, this only respects the vector space structure. So I would further require the diffeology structure also matches. So in the sense that this is an inclusion of a subspace, and this is a projection onto a quotient space in the sense of diffeology. This is very natural condition, right? And you can prove a very classical theorem also holds there. So which says when this short exact sequence splits, right, in the language of module theory, you will see. So the following, given a short exact sequence, the following are equivalent, which says if you have a map, the first one says if you have a map backwards, such that from V3 back to V2 and then go back to V3, it's identity, which is equivalent to have a smooth linear map backwards here. So if you go from V1 to V2 and then you go backwards, you get identity, which is also the same as the middle one is actually the direct sum of the two boundaries. And this one is just the inclusion of into the first component. And that one is the projection onto the second component. Okay. So you might be curious about, because for vector spaces, every short exact sequence always splits. What about diffeological vector spaces? If you have some experience with topological vector spaces, you know this is not always the case. And so the same is true for diffeological vector spaces. And the example is the one I have mentioned earlier from Boreal's lemma. But to be more, precise for some results, let me first of all mention one thing. So the thing says in this way: every linear subduction has a global lifting for plots of a domain. What it means like this one. So let me just compare this with a general theory. So given a diffeological space, if this is a quotient, okay, and these are just diffeological space, so I write ds for them. So in the theory of diffeological space, or you say in the theory of sheaves, so it just means every section you need a sheafification of that. Just means you can have an open cover of it, and each of that would lift to this x. Okay, but for diffeological vector space, the thing is much better. So if this is a diffeological vector space, then you can have global lifting. You don't need the shiftification anymore. So this is what this proposition says. This is my result. Okay. And what it tells us, it will tell me in this way. Okay. So previously I already said that this is Boreal's lemma, says given a function, if you take all its derivatives at 0, you get this surjective map, and then you can take the kernel of it. And a generalized lemma just says what? If given functions like this one, right? A series of functions, you can put them together into a smooth function in this way. Because linear subduction always has a global lifting, you can first of all check this is a quotient space, and moreover, you can lift it. And by lifting it, it just means you have a map. This is smooth, just means a joint map. This map is smooth, which matches the generalization of Boreal's lemma. Okay, so this the previous thing is just said. Generalized Boreal's lemma just said this map, this one is a short exact sequence of diffeological vector spaces. But the interesting thing is it does not split smoothly. So I'm not going to give you the whole proof of it, but I would roughly tell you how I proved it. The thing is, I take the D topology because these are diffeological vector spaces. Now I can take, or I should say diffeological spaces. So I can take the D topology of these. So I can understand the D topology of this one and the D topology of this one. And you can check that the D topology of this one is the same as the product topology. And we could also have some understanding of this topology. And you can check there is no continuous map back. It's impossible. If it splits, then you must have a smooth map backwards, which would be continuous after taking D topology. And it should have this composition as zero identity, but it's impossible. So essentially speaking, I just take the question is in diffeology, but I solved it in topological vector space. Okay, so this is how I proved it. I'm always looking for a smooth proof, but I couldn't find it. If you guys could find one, I would be very happy about it. Okay, so but what does this mean? This just means short exact sequence do not split. So we can develop homological algebra on it to clarify all these non-splitting short exact sequences, right? Which could be calculated by x to 1. But to calculate x to 1, there are two ways to do it. Either use injective resolution or projective resolution. So as I mentioned earlier, for diffeological space, you have a shift theoretical understanding of it. From shift theory, actually injective resolutions or injective objects should be studied first. So I searched for injective objects, but I could not find many examples. So then I was a bit frustrated. But then later on, I was thinking, how about projectives? And the interesting thing is you can find enough projective objects. So let me start by what is a projective diffeological vector space. It's defined in the usual way. So we call something is projective if for any linear subduction, it just means it's a diffeological vector space, it's quotient, right? And if you take an arbitrary smooth linear map, you can always find a smooth linear map such that this diagram commutes. Just means this one composed with this one is this one. Okay, so this is called projective. It's you can compare it with projective modules. It's the same definition, but now it's in the category of diffeological vector spaces.
So can I ask just to clarify? Yeah. Can you remind me what subduction means?
Oh, it just means quotient.
So it's surjective, and it belongs to your category.
Yes. Yeah. You can just think of it's a quotient map.
Okay.
Something like that. Yeah.
Okay, thank you.
Okay. So the thing is, I need to produce as many projectives as possible, right? Then I can do homological algebra, because homological algebra, you need enough projectives. So the first thing is I can take what is called a free diffeological vector space. So it's, I'm not going to give you all the details, but just to tell you abstractly, given arbitrary diffeological space, you can always find a diffeological vector space, which is defined as a vector space. It's very easy. So take each element in X, you just get a copy of R, okay? This is your vector space. And you can have a smallest diffeology, vector space diffeology, because you want to make it not a diffeological space, but a diffeological vector space, such that you want to put the information, diffeological information of X into this diffeological vector space. So there is a canonical map from X into Fx. You just send in the element X to the element 1 in this R related to this X, right? So maybe I should write this Rx, which is each one is isomorphic to R. You want to have this copy 1 inside here. So in this way, you just put the diffeological information into this diffeological vector space. Okay, so I just tell you it exists. You can do it by construction. You can construct what exactly the diffeologies are, and then you can check the addition and the scalar multiplication are smooth. But it's generated by this one. So the interesting thing is, for any smooth manifold, this Fm is always projective. Recall, projective is just you need to do this lifting. But for a manifold, so here by a manifold, I always mean second countable Hausdorff manifold without boundary. So in particular, you have smooth partition of unity. You exactly use smooth partition of unity here to get the lifting. Okay, so this is proved by the partition of unity.
Just a moment, Enxin.
Yes.
So that the Fx is the space of the total space of trivial bundle.
Sorry.
Bundle. So,
sorry, could you say that again?
So Fx is the total space of the trivial line bundle over X, and you map so that's any section of it you can identify with a function. Now you identify by taking constant function, right? X to g equal 1. And then you have the actually that question I already think a little bit, but that already mentioned in the book by Starship. Yeah, when he wrote characteristic classes 50 years ago. Yeah. So he considers that a space of the he want to consider that a very meaningful has a global coordinates. That means embedded in some vector space.
Yeah.
That way, and that's I was actually thinking that this embedding must be smooth. Yes, that means you need smooth structure on that Fx.
Yeah. Yes, definitely. You need a smoothness, and
so
I will actually my later on stuff will be related to maybe some of the questions you are just said.
So that Starship has that idea, but he didn't know that time before.
Diffeology. There is no diffeology. Okay. Yeah. Yeah, that's right. Now we have appropriate language for that. And here it's just manifold. And moreover, you can see these are orbifolds. So this here I just means R2, and here Cn just means the cyclic group of order n. And you can have a linear action of the Cn acting on Rn, the linear action. And the origin would be a point where the orbifold structure is. And you can actually show that this is also projective, and the same as this one. And the plus minus 1 is just means the group of 2 elements. You can act on this by sign, right? Act on it by sign, and you get orbifold, and the free diffeological vector space on that, and they are also projective. So you have many projectives, so that's why it's good. And moreover, you can prove this is a homological algebra language. You have enough projective. So that's why you can do homological algebra on diffeological vector spaces. So that's the very interesting thing, but I'm not going to give you a proof. It's abstract using diffeology structure. But anyway, so I need to be a little bit quick. Yeah. Okay. So another important thing is you have the structural theorem for projectives. Projectives are very abstract, but you can somehow make them to be concrete using this theorem. It says every projective, they are always a smooth direct summand of direct sum of FUs. So what does it mean? It just means you take many copies. Usually it's many copies of FUIs, where UI are open in some Euclidean space, but they could be in different dimension. And then you write it as a direct sum of, maybe I say A and B. Then both A and B are projective. So it just means that every projective is a part direct summand of direct sums of these things. So usually we prove things for the FUs where U is open in Rn. And then you pass to direct sum and direct summand, and then you can prove results. So for example, you can show that the D topology on every diffeological vector space, it's always Hausdorff. You don't know what a general projective is, but you first prove it for FUs always has the property, and you can check the direct sum also has the property, direct summand also has, and so is every projective. So this is how we proved this one. Okay, and another surprise is if you compare this theory with the usual module theory. So in module theory, we know the free modules are always projective, but now we can see not every free is projective. So for example, the irrational torus, this example, T alpha, we already know it has no topology. In other words, it just means the open sets are the empty set and the T alpha itself. So it's not Hausdorff. But you can still take the free diffeological vector space generated by this T alpha. So this one, it could not be Hausdorff. The D topology could not be Hausdorff. So it's not a free. It's not projective, sorry. It's free, but not projective. So it satisfies this one. And very interestingly, recently, my collaborator and I have, Yang is also here. We proved that the projective diffeological vector space are good because the D topology makes every projective diffeological vector space into a topological vector space. And the proof is similar. We essentially use this structural theorem and prove essentially for this FU, then pass to direct sum and direct summand, and then we have results for projective diffeological vector spaces. But the funny thing is, in general, this is not true. In other words, given a, so let me just say, given a diffeological space, you take a D topology, you get a topological space, right? But if you get a you start from diffeological vector space, you take its D topology. It's not necessarily a topological vector space. Sorry, I should say it's not necessarily a topological. Oh, sorry. It's not necessarily a topological vector space. You would first say it should be, right? But it's not. We just got some concrete examples. So the key thing is, in general, we know that this functor, this actually gives rise to a left adjoint D from diffeological space to topological space. It's a left adjoint. So left adjoint just means it behaves good with co-limits, but for limits, it's not so good. So in particular, we could not have this one. So this one is not necessarily the product topology. Okay, so this is a problem, and you can find a concrete example for that. We really like to understand in the general case when this would fail, but it's hard. If you guys are interested, we could discuss more about it later. Okay, so let me go on. Oh, Okay, sorry. So let me go on. So now I'm going to the question maybe Van just asked. So I'm going to do bundle theory, but the bundle is slightly different from the bundle in differential geometry. So in differential geometry, usually every bundle is locally trivial, but I want to get rid of this condition. This is because for a diffeological space, you can always get the tangent bundle, and this tangent bundle is no longer locally trivial because diffeological space could be very, arbitrary. It could be not locally Euclidean, right? You can be very strange, and the tangent bundle is no longer locally trivial anymore. But nevertheless, we could still make the following definitions. It says a smooth map between diffeological space is called we call it a diffeological vector pseudo bundle. So we leave the vector bundle for the locally trivial, or at least plot-wise locally trivial bundles. And I use DVPB, the small letters, to denote diffeological vector pseudo bundle. If the following three natural conditions hold, so the first one is every fiber should be a vector space. So here I just here in this talk, I always mean vector space over R. Of course, you can also take a vector space over C. And if you just consider just the bundles, not the complex bundles, some things should be okay. And moreover, you want the fiber-wise addition and the scalar multiplication to be smooth. It's very natural, right? And another condition, you want the zero section to be smooth at least. You might not have other sections, meaningful sections, but at least you need the zero section to be smooth, right? So in particular, this just means this would imply B is a quotient space of E. In particular, this third one, okay? Okay, so you can compare with the classical definition of bundle. We just get rid of the local triviality. So what's good for it? So first of all, it encodes the tangent bundle of a diffeological bundle. And moreover, you can generalize all the operations to, so here I mean, what do I mean is if I fix the base space B, I take all the diffeological vector pseudo bundles on B and the bundle maps over B, and then I get a category, right? But you can also move the base, change the base, right? And you can have these the bundle maps between different diffeological vector pseudo bundles with different bases, right? You get another category. And you can generalize all the usual operations. So the usual operation, as you can just imagine, for example, the product, the direct sum or Whitney sum, the tensor product, the exterior product, symmetrical product, for example, and for example, the home bundle, what else? The dual bundle, for example, and so on. You can, and the pullback, for example, the restriction of the bundle, yeah, something like that. All the usual operations you can generalize to these diffeological bundle, diffeological vector pseudo bundles. Okay, and moreover, this category, if you have the common base, and you can also check it's additive but not abelian. So in particular, if you take a B equal to a point, you just get back the previous diffeological vector space theory, right? Okay, so what's good is you can also ask the same question as we did for diffeological vector pseudo bundles over a fixed base space, right? So we already know if B is a point, not every short exact sequence splits. Of course, the same phenomena happen there. So in particular, you can also take projective objects there, right? Projective objects. So the good now, some magic comes. The magic is somehow called another operation there. So if you compare this with algebraic geometry, you know, algebraic geometry, besides pullback, you also have push forward. So this is what I'm going to talk about here, the push forward operation. So it means given a diffeological vector pseudo bundle here, given arbitrary smooth map here, and you can construct a diffeological vector pseudo bundle on this side. So you can imagine, like, for example, this B prime, if it's a pointer here. Let me just mention, let me just denote this map, smooth map by F. So what you want to do is for each X inside F inverse B prime, you might have many pre-images. And each of them, when you take up, it's a section, right? So I would have this EX. I direct sum all these EX. And then I take all the B prime inside B prime. And this is my E prime as a set. As a set, it is this one. And you can give it a suitable diffeology, which encodes this structure into this structure. Okay, so this is called push forward, but because I don't have enough time, so let me be a bit vague. Just you can imagine, you can push this structure into this structure. So the amazing thing is the push forward. Let me first give an example. This operation makes sense. If you take this side to be a trivial bundle, you push it along this map from B to a point, then you should get a diffeological vector space up. What is it? It's just the free diffeological vector space generated by B, which I defined earlier when constructing examples of projectives, right? So this example is quite stimulating. And moreover, you can prove, because I have already said you can do homological algebra on this. Oh, sorry, I used the wrong letter here. So I should say it's a diffeological vector pseudo bundle over B. You can do homological algebra. So first of all, you can define projective there. So for each B, you have projective there. So you can talk about projective diffeological vector pseudo bundle. So the result is, if you take a projective one, push forward, you get a projective one here. Moreover, you can prove if this is a smooth manifold, this is a vector bundle in the classical sense, which is a locally trivial vector bundle, and E is also a smooth manifold. And it is projective, okay? So in this way, So in this way, what do you get? You get many projective diffeological vector space because you just take a classical diffeological vector bundle, a classical vector bundle in differential geometry. You push forward along the trivial map to a point, and you get a projective diffeological vector space for free. So you get many amazing things, right? Okay, so at the end, let me give you two very curious identity about diffeological vector spaces. It's a splitting of diffeological vector space. So let me start by this one. So by the covering space. So Sn to Rpn. Okay. So we all know from algebraic topology, the fiber is Z over two points mapped to one point. It's a covering space. So in particular, what do you get? So if you have this Sn cross R, right? We know we could push it now. So let me just do it in this way. So this is R0. So I could directly push forward it to this R0, right? And by the previous example, we already know it's Fsn, right? If I do the push forward here. But you can also do push forward here and then push forward here. Here, if you calculate, you would get two parts. One is, oh, sorry, I shouldn't say in this way. But the thing is, if you take this one, then you take this one, you get the same map, right? But the thing is, you have another way to do it. Oh, Yeah, sorry, I'm a bit sloppy here. So if you also take this one, go to R0 point, you would get this f of Rpn. So in particular, if you have such a map, then you have if this is a subduction or a quotient map, you automatically have a quotient map here. And you can use this bundle theory to calculate what is the kernel of this. And you can check there is a bundle theoretical meaning of a certain bundle inside here. So here, what do I mean is the trivial, the canonical line bundle on RPN. So we have this canonical line bundle RPN, right? It's defined by gamma n1. So if I push forward it to R0, I denote it by V of gamma n1. Okay, so this is a push forward. You can check push forward. You can check this one direct sum, this one is exactly this one. And these two pieces, they would correspond. Why this is 2? Because it corresponds to this fiber. Okay, so you have this isomorphism. So in particular, if you take n equal to 1, what do you get? This is S1, but RP1 is also isomorphic to S1. So that means you have FS1 isomorphic split FS1 out of a V of gamma 1, 1. So this is, if you view S1 as RP1, you have the canonical line bundle there. So you can split out a gamma 1, 1 there. Because you can split 1, so you can split finitely many S1, V gamma 1, 1. So I don't know. So I just randomly say something. It probably doesn't make sense. I was curious about, is there any maybe physical instruction about it? For example, if this is some kind of like a particle, you can somehow have the particle and you can split out some other kinds of like particles or something there. Does it happen? Sorry, my physics is not so good, but maybe there is some kind of like a phenomena there. But anyway, so this is the first example I want to talk about. Another funny example, so let me be slightly quicker, is this one. But this one is somehow complicated. I will explain a little bit later, but anyway. So in particular, if you take n equal to 1, the same as the previous case. So this is also FS1, and you can check this is also FS1, and this is 2 copies. So altogether, there are 3 copies of that. So here is also S1, but I didn't say what it is. But let me just roughly say it's also the same as this. When n equal to 1, it's the same as the canonical line bundle on S1. So in particular, you will have this kind of like isomorphism. So to me, these are infinite dimensional splittings of diffeological vector spaces. And it's related to bundle theory. It's curious. Oh, so finally, let me mention about how do I get this one, roughly, how do I get this one? So this one is done in this way. So I still consider this covering space, okay? This covering space. And now I consider tangent bound there, tangent bound, TSM. So from, for example, the Milner-Stashev book, we know if you direct sum a normal bundle, it's a trivial bundle, right? Sn cross Rn plus 1. And the normal bundle is also trivial, which is Sn cross R, right? If you push forward, so push forward is actually a left adjoint, so it would preserve these direct sums. So in particular, this could be viewed as Sn cross R direct sum and plus 1 times, right? So when you take push forward along this R0, you would get f of Sn and plus 1, okay? And on the other hand, you will get Fsn direct sum of this, using my language, if TSN, right? Tangent bundle, direct sum, the normal bundle. it will be a trivial bundle of this rank. So the same thing, you do it for the RPN. You take the tangent bundle, and the result is the tangent bundle. If you direct sum it with the normal bundle or with a trivial bundle, you will split it into the canonical line bundles, n+1 copies of canonical line bundles. And then the third step is you compare this tangent bundle and this tangent bundle. Actually, you can take the push forward there, and you can use the bundle theory to understand the kernel here. The kernel I denoted by V pi. It's the same rank as this tangent bundle, but it's slightly different. But when n equal to 1, it's very easy to verify. It's just the canonical line bundle there. So eventually we get these kind of things. So I got these identities. I found them very amazing, but I don't know. Maybe there are some deeper theory there, or maybe it has even some connections with physics or something. But hopefully you guys could figure it out or help me to figure it out. So I think that's all for my talk today. Thanks all for listening.
Thank you very much, Enxin. Yeah, let's thank the speaker.
Thanks.
Yeah, Enxin, I have a question that may be related to the question that Igor asked at the beginning. So you say about the topology, that is the how to say, the the topology on infinite dimensional manifold.
Yeah. Yes.
So that is a small let diffeology. That's a
smallest. Oh, you mean this one? This one? Yeah. Oh, yeah. You mean topology, the general one?
The topology, yes, the finite topology. That means that's yes. But how to say, that is also interesting. Then Igor conjecture, that is the in Banach space that is generated by norm, right?
Yes.
But for people working on the kind of the machine learning, then we are interested in the not D topology, but on the weaker, that concept weak topology, you know?
E topology?
No, weak
topology. Weak topology. Yes.
That is a conceivable on vector space of sign fine measure. Then it has a Banach structure, yeah. But if the how to say, of course, if you consider the X is a separable, metrizable, then it has then you define that is topology smaller, and actually that's very interesting. That is so I think that you should you never try to study such kind of the topology.
I think there are some worked out examples by maybe Jordan Woods and Patrick and some other people. There are some comparisons between them, but it seems there is no, nice theorems really saying under what conditions they always match. Even like for so previously Igor mentioned about those fresher manifolds, right? So there is also kinds of like things called what's that called? Philological space. If you have heard of Philological space. So you see diffeology. Diffeology is somehow, you see, it's just one side. So you just map something in, right? Map something in. So the weak topology is somehow mapping something out. So it's some kind of like a dual, right? Mapping in, mapping out.
Right.
So the Philological just means you want some balance between this and this. So this is Philological. But even for Philological space, you can define two topology. One topology using this, one topology using this. And they in general do not match. So that's a difficulty. That's a difficulty. I think the differential geometers or the algebraic geometers, they prefer this side. So this side. And the diffeology prefers this side.
One side.
So each one has its advantage and disadvantage.
Right.
And there is no very nice theorems between them. I wish I could find one. I tried a bit, but Yeah, unless you have a very concrete example.
Yes, okay, I should tell you because I have to say there are, for example, book by almost 1,000 pages by Villani Optimal Transportation, right? On this topology, gradient flow, but they are very theoretical one. And in machine learning, one interested in more concrete and finite dimensional.
Yeah.
So that's I am interested in the theoretically. One that is when you restrict to finite dimensional case, do you have really something new or not? Yeah. So I think that's maybe that diffeology can be shown, but let us exchange per email because we have another question to you. That by Basia, what should be a simple example showing that the additive category of the diffeological vector space fail to be abelian?
Or fail to be abelian?
Yeah.
Okay. So the abelian actually it's very easy to fail because so I can even take it for diffeological space. It's not abelian, but the same situation happens. So you see, so the abelian property requires what? So it requires the what's that called? The monic should be a kernel, right? Monic should be a kernel. Just mean the monic is just means if you have two maps mapping in, if composed they are the same, then these two maps must be the same, something like that, right? But the thing is, for this one, even this is injective, but the diffeology, you can put many diffeologies on it, many diffeologies. Not necessarily the sub-diffeology. In particular, you can put a sub-diffeology on it. Sub-diffeology would be good enough, but you could have some weaker, like a smaller diffeology than the sub-diffeology. You can also make this to be true. The monic just means this map is injective, but with no conditions on the diffeology there. So that's why it gives rises to non-abelian. It's almost abelian, but not really abelian. So here I can take this X to be a diffeological vector space. Here it's just a subspace of the vector space, but it gets the diffeology smaller than the sub-diffeology. And it's still monic, but it's not a kernel. So it's somehow like a categorical thing. It gets wrong. It gets wrong. It's not the categorical. This monic thing is too weak. It's too weak. So you need to put stronger conditions here. Then you can make it to be true. So that's why it's, although it's additive, but it's stronger than additive. I forgot the proper name on that. I think on the references there is a proper name on that. I think couldn't remember exactly. Something additive. There is another adjective for this additive thing, and it is satisfied. So that's why you can do homological algebra. If a general additive category, you couldn't do much, right? You need somehow stronger conditions on it. Yeah.
Could I ask a question?
Hey, yeah. Hello, Professor Morris.
Hi. Firstly, can I thank you for a beautiful talk? Very, very interesting. And you clearly have done some very nice stuff. I come with this from the intuition from topological groups, topological vector spaces, and abstract category theory. Now, for example, from the abstract category theory, I know, as you just were mentioning, monic is not usually strong enough for what we need. Anyway, what I wanted to say was really, if the definition pre-DVS is right, and if the definition projective is right, what do I mean by right? I mean right in the categorical sense, then the free object ought to be a projective.
Ah, I see.
And the only example you gave was in the non-Hausdorff case.
Yes. Oh,
And
actually, I can give another example, which is Hausdorff, but not projective. That's in our paper here.
Okay.
It will be ready soon. I can tell you if you want. I can tell you what it is.
That's not the right question in my mind. In my mind, the right question is, when is a free object a projective?
Oh, yeah, you have
And
asked
I
a
think
very good question.
That would be very rich, I think.
Yes, yes, you asked a very good question. I really wish I could answer it. So the conditions I got, first of all, it has to be Hausdorff. And second of all, it has to, the D topology has to be a topological vector space. But I didn't find if there are some more conditions I have to add. Thanks, you asked a very, very good question.
Okay, the other thing is, just at the end, you were talking about the free object on S1 and getting some surprising, what seemed to be surprising then. There's a very rich theory on free topological groups. And if you have a look at there, the free topological group, for example, on the unit interval, has as a sub-object the free topological group on the square or on any product of intervals. So the free, when you make it into a vector space, sort of geometrically, you fill the hole. But in any case, these results I don't find quite as surprising as you do. I think if you ask yourself, if you have a look at what's done on free topological groups in terms of embeddings and understanding that, maybe there's many more results like this that you can get.
Yeah, thanks for mentioning about it. Yeah.
So if you look on my publications, there's some that should tell you that that's related, but I mean, I'm not the only one who wrote on this. Many people have written on it.
Okay, thanks. Thanks. It's very helpful. Thank you very much. Yeah, I will definitely look for these results. Thanks.
So somebody have more questions?
Can I ask just a simple clarifying question? Maybe it's about these free diffeological vector spaces.
Yes.
Can you identify this construction with any classical construction, like take distributions? So if M is a manifold, and then Fm is like space of distributions on a manifold or something like that, or space of measures, Dirac measures, like linear.
Let me just think a little bit. I think I once thought about these things, but I think if I do it correctly, but I'm not 100% sure right now. Maybe these are distributions. If you take a dual, these are distributions. But let me just think more about it. Distribution
so you want the
on X, I think. So let
L,
me see.
L infinity.
L infinity just means smooth linear. Smooth linear.
Oh, okay.
All the smooth linear maps, not the L infinity in the sense of function analysis. Yeah. So I think it's this one. This one should be true, but I'm not 100% sure. In general,
can I suggest that what one is really when one knows by the adjoint functor theorem, the free object exists, and the free object is constructed there by all possible mappings, roughly speaking, all possible mappings.
Right.
When you take the group case, you find you don't need all mappings into all groups. For example, the unitary groups are enough, and so on. And therefore, these examples are when do you have enough mappings to really have something rich enough to give you the free object.
Right. Yeah. Yes. And in this case, it's actually lucky. So I didn't quite use this general results, but you can construct by hand. But in general, yes, Professor Morris, you are right. you take all the maps, but in good cases, you just need some certain ones. That's already enough. Exactly.
Hopefully, there's enough concrete examples that one knows that will be enough.
Right, right.
And if you can use that information to identify this free object with something which is, you know, kind of classically known, then you know, I think that's worth including in some of your papers if you can find that identification.
Right, right. Yeah, up to now, I don't know. I mean, but for elements, it's very easy because you just write them as formal additions. It's a finite addition, for example.
Well, that's why I thought that this may be like linear combinations of Dirac deltas on the original manifold. Yeah.
Exactly, exactly.
But it depends like because I guess you need to take some kind of completion, and then it depends what like if you're thinking in terms of topological vector space, exactly what kind of completion you take that you generate different spaces.
That's right. So I think as a general result, but I couldn't remember exactly. But I think roughly speaking, you take the dual thing, then you would get back to distribution, something like that. Yeah.
Okay. All right. Thanks.
Thanks for the question.
So, Enxin, I didn't see the reference at the end of
your
talk.
I forgot to write down the references. So actually, there are a few of them. So one is so this one we will be ready very soon. So ready soon. Okay.
Yeah.
Ready soon. And this one I have many W's by myself, but this is my HHA. So homology homotopy applications. So this is 2015, I think.
Yeah.
And this one is 2019. It's on the Pacific Journal of Mathematics. So it's about diffeological vector spaces. The title is called diffeological vector spaces. Okay, so and there are others. For example, this one is it's not published yet, but it's on archive. It was accepted by Israel Journal of Mathematics. It's called exterior bundles. Exterior bundles in diffeology. So I think it's also quite interesting. And the rest, especially this one, and these things, it's in my preprint. I just submitted it. So it's my preprint, but it's on the archive. I think I haven't put the latest version. The latest version, the previous version contains these results, but not this one. This one is in a later version, but I need to update the later version. Yeah, thanks for asking.
So Enxin, could you put how to say this reference in at the end of the slide and send me, and we can put on the website.
Yeah, I will put it there, and then I will send you the copy of my slides. Yes.
So correct it. Yes. So thank a lot of if I forgot again. Okay.